Alrighty, here's the do now. Please pause the video and give it a good try. So the first thing I noticed is that u is either going to be cotangent or cosecant. The reason why we use cotangent as u, let me use a different color, as u, is because when you take its derivative, you're going to get negative cosecant squared. Now that's almost perfect because we have a cosecant squared right here. And if there was a negative right here, then we would actually be able to create a direct substitution to change all of this to du. So in order to make a negative, we got to multiply the cosecant by -1. But in order to undo that or make it legal, we're also going to have to multiply a -1 on the outside of the integral. So when you do this, you're going to end up with, so all of this is going to be, and as illustrated, all of that equals du. All of this became du. So what you're left with is cotangent to the 8th power. Now, given that we know that u equals cotangent, we can change this now and change it to the following. So this becomes negative, and then you can see it, negative u to the 8th power. And then when we actually do this, it's going to end up being 1/9 u to the 9th plus c. And when you plug back in, because you know this, you remember that u equals cotangent, then you should end up with 1/9, and then, let me just go ahead and write it, 1/9 cotangent to the 9th of x plus c. Alrighty, so that would be the first problem. Let's do the second problem. For the second problem, same logic. So u is either going to be, because we know this is going to be u substitution, we either going to let u equal secant, or we either going to let u equal tangent. So the derivative of tangent is just secant squared, which would be a problem because secant squared doesn't evenly go into the 7th power. So let's consider the derivative of secant. If you let u equal secant, then as you can see right here, and probably don't want those to be hovering over. So when you let u equal secant, you notice that you're going to get secant tangent. So if you, at the first look, this doesn't actually look ideal. But if you actually use this trick where you take one of those secants out of here, so making it secant to the 6th, and attach that secant that you took out next to the tangent, then we have a perfect substitution. Because when we did the whole thing, we ended up saying that du, let me use a different color, we said that du will now equal secant tangent of x dx, which is exactly what we have here. So you have the integral of u to the 6th, which is 1/7 u to the 7th plus c, and all you have to do is plug back in, and let me move it so we can see the plus c. All you have to do is plug secant back in there, so you're really going to end up with, when you take this guy and put it right here, 1/7 secant to the 7th plus c. So that was that problem. So let me get ready for the next problem. Alright, so let's do the next problem. We have, and let me go ahead and highlight as I read it. We have x plus 2xy plus y squared minus equals 2, and then at point 1, find the derivative. So let's do this problem. Alright, the first step is to just take the derivative. So whenever there was an x, I did a regular derivative, but whenever there was a y involved, I attached the y prime. So the derivative of x just 1, I pulled the 2 outside so I don't have to deal with it, and then I did the product rule for xy. So the derivative of the x just 1, which is why there's nothing here, and then times y, plus, and then derivative of the y, which is 1 as well, but we have to attach a y prime, times x. Then I did the regular derivative of this one, so negative 2y, but because of it's a y, we did y prime. And then the derivative of 2 is just 0. From here, we now do the, we continue. So everything that has a y prime needs to be left by itself, and everything that doesn't have a y prime needs to be on the other side. So let's do that right now. So I probably want to apologize for the horrible quality, but So I pretty much did what I said I was going to do. This had a y prime, this had a y prime, so I left them here. So 2xy prime minus 2yy prime. And then the 1 and the 2y, because it didn't have a y prime, I moved them to the other side. So negative 1 and negative 2y on the other side. Now what I'm going to do is I'm going to divide both sides by whatever this is when I factor out a y prime, which will be 2x minus 2y. So what do we have here? We have, let me get green this time. Y prime will equal, oh, that's a strong green. I don't like that. Let me switch back to, what happens if I do black? Okay, I like black. So we pretty much took this entire thing and divided by the factored version when y prime is factored out, which is 2x minus 2y, which will leave you with y prime. And then do the same thing on the other side. So negative 1 minus 2y divided by 2x minus y prime. And all we now have to do is plug in negative 1 and 1. So we're going to get on the top, I'm going to do this in real time. We're going to get negative 3 on top because negative 1 times 2 times 1 is just negative 3. I say negative 3, but I put negative 1 for some reason. On the bottom, we're going to get, wow, that's 0. That's no good. Is an undefined an option? Let me check real quick. Alrighty, something somewhat funny just happened. So I kept checking my work, and all I saw in my view was this, and this, and I thought to myself, I'm pretty certain I didn't make a mistake. There seems to be a 0 in the denominator. That implies that there's no answer. And then I kind of zoomed out a little bit, and then I saw option E, which is definitely made my day, that thing is right here. Alright, so I didn't make a mistake, but I kind of doubted myself. Shouldn't have done that. Alright, and then the last one is a lot easier because you simply take the derivative of sine. Derivative of sine is cosine, and then you plug in pi over 3, and cosine of pi over 3 is 1/2. So this will be it right there. Alrighty, that's to do now. Let's continue. Alrighty, for this one, students will use the Riemann sum to find approximate values of definite integrals. So over here, let's talk about what an integral really is. An integral will get you the area underneath the curve. So you're looking for all of these areas, and the integral will actually get you these areas. What we're going to do is we're going to find the areas using the fact that we understand how rectangles work. The area underneath the rectangle is going to be the length times the width. Over here, because we have a velocity graph and that's a time graph, you can say that distance equals velocity times distance equals r, that's rate times time. Alrighty. Also, the units work out here as well because distance will equal meters because time has seconds, rate is meters per seconds, the seconds cancel. Essentially, when we have a rectangle, all you really do is width times length, and then you get all of this area that way. And that's pretty much what the Riemann sum is all about. Let's talk about the definition of a Riemann sum. So over here, what we've learned in the past is to use the trapezoidal rule, where you use a point here and a point there, and then you create a trapezoid, get an area, and then you do the same thing right here, same thing right here, same thing right here, and then add all these trapezoids together. But for the Riemann sum, we don't use trapezoids. We just use rectangles. So you notice that we have rectangles, and because we're using rectangles, we're going to get two types. We're going to get rectangles that over here, it seems that this rectangle is going to be a overestimate, and then over here, this rectangle seems to be an underestimate of the thing. Let me zoom in on that. The reason why this rectangle, and let me also use a thicker pen. The reason why this rectangle will be an underestimate is because most of it is underneath the line, underneath the graph. And this one will be an overestimate because most of it is above the graph. So you're gonna get, if you do this, you're gonna sometimes get overestimates, underestimates, and we're also gonna be using a third type, which is a midpoint. So let's talk about it right here a little bit. So the Riemann sum, the way it works is you pretty much are going to have the function, which we're going to call the height, times the width, which is the difference in x, and you're going to add all of them together. So that's the basic definition of a Riemann sum. So in the picture, what that would look like is you create a bunch of rectangles. This is the width of the x. This is the f of whatever x. If you're choosing to do the left point, that'd be f of a. And then if the right point, that would have been like f of x1, depending on where you want to standardize your rectangle, how high it's going to go. And you're going to have 4 of these. So add this one to this one, add this one to this one, and add this one to this one. All right. And that's pretty much very similar to this one, except what an integral does. It uses an infinite number of rectangles. So it wouldn't have 1, 2, 3, 4. It would have an infinite number of rectangles, which would make that a perfect value. This will get you the exact, it will not give you an overestimate or underestimate, it will get you an exact value. Before I move on, let me just sum it up a little bit. In order to get the Riemann sum, and the Riemann sum, we're talking about the sum of all of these rectangles right here. Let me see if I can erase it so I can expose those again. Da-da-da. Okay. So in order to get the Riemann sum, you have to add all of these rectangles. And each rectangle, it is the function times dx. So f of these values. So if using the left point, it's going to be this value, this value, this value, and this value. Let me use a different color. This value, this value, this value, this value. If using the right point, it would be, let me use a different color. This value, this value, this value, and this value. It's always going to be 4 values in this example right here. So those go right here, and you're going to get an f value. So you're going to multiply the f by however big this is. And essentially what that's going to be is going to be b minus a divided by how many you want to do. Like if you want to have n equals 4, you would make that equal to 4. So b minus a divided by 4. So that's how you get the Riemann sum. It's supposed to simulate this process right here, but less accurate. So I'm going to reiterate what I mentioned before. So the Riemann sum, we have 3 types. We have a left, a right, and a midpoint Riemann sum. And the left Riemann sum pretty much means that if you have all of these values, you're going to be using the left point of the rectangle and to plug into that f. So we had like the summation of f of some value times delta x. What you're going to be plugging into here, if it's the left one, you're going to be plugging in this one first, then you plug in this one, then this one, then this one, then this one, then this one, and that's it. But if you were doing the right Riemann sum, you would plug in this one, this one, this one, this one, this one, and this one, which is why you see that these points are the ones that go along the function. It's not the left one. And then when it comes to the midpoint, you would have to figure out, so that one's a little bit more annoying because you actually have to figure out what that point is. You have to find out, let me lower this, the side of this. You have to find out what these points are, and then you have to plug in those. So if you have from 0 to 4, and then you want 6, so that is 0 to 4. 4 minus 0 is 4 divided by 6, and that's going to be give you 2/3 or 0.6. So essentially you have like 0 and then 0.67. You're not going to use either one. You're going to find out what's in between. So that's going to be, I don't know, 0.33. So it's the value in between the two that will go into right here, that f. And that's it. See you guys tomorrow. Oh, before I end the video, the book will talk about upper and lower Riemann sums instead of saying left and right. At which point, whichever one gets you the higher number. So if you do like the right Riemann sum and the left Riemann sum, and this gives you like a value of 3, and this one gives you like 3.5, then the left Riemann sum got you the upper, and the right Riemann sum got you the lower Riemann sum. So they're just using different words. They don't straight up tell you to use the left or the right. They want you to find the upper or lower. Just do both, and then the upper one would be the bigger number would be the upper. See you guys tomorrow.